Hello everyone, welcome to our new exciting video series of Applied Machine Learning with KerasCV and KerasNLP. My name is Wei and I'm a developer advocate from Google ML team. In this new video series, we're going to explore how to leverage the two powerful Keras domain libraries to tackle common computer vision and natural language processing tasks. Since these two libraries are based on Keras, we're going to assume you are familiar with basic Keras APIs and have a solid understanding of fundamental machine learning concepts. Before diving into KerasCV and KerasNLP, I want to introduce you to a very exciting new feature from Keras Core. This fantastic feature has a modular backend architecture and allows you to run Keras code on top of arbitrary frameworks, including TensorFlow, JAX, and PyTorch. It also enables you to seamlessly integrate Keras components like layers, models, or metrics as part of low-level TensorFlow, JAX, and PyTorch workflows. We'll be releasing some videos dedicated to Keras Core in the future. For now, you can think of Keras Core as an abstract layer that allows you to transparently swap executing backends without changing your modeling code, like what's being shown here. If you want to learn more about Keras Core, feel free to check out the announcement link below. You may be asking, why are we even talking about Keras Core in this video series? Since this is a video series on KerasCV and KerasNLP, right? Good question. The reason is that KerasCV and KerasNLP, which of course uses Keras as a core, are already compatible with Keras Core. So you can try different backends in your CV and NLP applications today. By default, KerasCV and KerasNLP use TensorFlow backend. There are two ways to make the change. One way is to use the Keras backend environment variable. For example, on the left, we are changing the backend to JAX by setting the environment variable in shell or in Python code. Another way is to set the flag in config files, as shown on the right. In this case, you need to change both the backend flag to JAX in the keras.json file and the multi-backend flag to true in kerascv.json or kerasNLP.json file, depending on which library you are using. Since the default backend in Keras Core is TensorFlow, I want to highlight that KerasCV and KerasNLP models are still compatible with all of your favorite TensorFlow features, including TensorFlow Lite and TensorFlow JS for inference on mobile devices and the browser, XLA compilation and TPU acceleration for fast inference, and dtensor for multi-accelerator inference, which is important for the latest language models with weights as large as tens of gigabytes. Now you understand how cool Keras Core is. Let's take a look at what KerasCV and KerasNLP can do for you. The last few years of machine learning innovations have greatly expanded our understanding of what's possible with machine learning. From breakthrough performance in classical benchmarks to the exciting new field of generative AI, it's critical to stay up to date with the latest models to be competitive. At the same time, state-of-the-art models have gotten increasingly complicated and often require expensive pre-training to be useful. That's why we have open-sourced the KerasCV and KerasNLP, the easiest way to deploy state-of-the-art pre-trained models for text and image classification, object detection, generative AI, and more. With these libraries, you will have access to cutting-edge models with a simplified and consistent API. Take a look at these two examples. You can fine-tune a BERT classifier or generate images from a text prompt with just a few lines of code. There are a lot of machine learning tasks KerasCV and KerasNLP can help you with. In this first video, we will take a quick tour of the unified KerasCV and NLP modeling APIs so that you can appreciate how easy KerasCV and NLP are in these common use cases. Let's start with KerasCV. So in this example, we would like to classify images as cat, a negative label, or dog, a positive label. The highest level model in KerasCV and KerasNLP is a task. A task, like image classifier, is a Keras model consisting of a backbone submodel and a task-specific layers required for solving a specific problem. Backbone models, in turn, are a set of reusable layers generally pre-trained on a separate task to extract highly informative features from the input data, greatly reducing the amount of labeled data and compute resources required to get competitive performance on your task. In this example, we use a ResNet architecture for our backbone to load models with pre-trained weights in KerasCV and KerasNLP. Use a FromPreset constructor with the name of a preset. In this case, ResNet 50 ImageNet is a 50-layer ResNet model pre-trained on ImageNet dataset. You can find a list of all available presets in the class.doc string or on keras.io website. Once we have created our backbone model, we pass it to the image classifier constructor along with the number of classes we would like to predict. After that, compile and fit the model like any other Keras workflow, and you're ready to go. KerasCV also supports object detection. This is a significantly more complex task than image classification because the model can detect any number of objects and must predict a class and a bounding box for each one of them. In this example, the blue boxes and classes are ground truth labels for objects in the image, while the orange boxes and classes are inferred by a KerasCV RetinaNet model. Despite this added complexity, creating an object detection model with a RetinaNet architecture is very similar to image classification. We again choose a pre-trained ResNet 50 backbone using the FromPreset constructor. The main difference is requiring labeled bounding boxes in the training set and specifying the bounding box format in the task constructor. After that, compile and fit the model like any other Keras workflow, and you're ready to go. Data augmentation is a critical pre-processing step necessary to maximize accuracy in computer vision tasks. In order to avoid overfitting to the lighting, cropping, and other particularities of the training set, it is important to rotate, noise, and even mix together the original images to increase the robustness of the training objective. For example, the flowers in the upper left panel are original images from the training set, and the flowers in the lower right panel are versions augmented by KerasCV. KerasCV offers a wide variety of augmentation layers, all in a simple API that can transform classification labels and object detection bounding boxes along with the original images. These include random flip for rotations, random augment for intensity perturbations, cut mix and mix up for creating composite images, and many more. Simply combine your desired augmentation layers in a Keras model and map over your dataset before training the model. Are you excited about generative AI? Sure we are. KerasCV provides that simple interfaces to the latest text-to-image models such as Stable Diffusion to generate novel images from your text prompts. Instantiate a Stable Diffusion task with a desired output image size and then call the model's text-to-image method with a prompt and number of output images. Here, we tried a photograph of an astronaut riding a horse and can't argue with the results. We're constantly adding more generative AI capabilities to KerasCV. Here are some advanced features we already support. Text-to-inversion is a method to teach Stable Diffusion models specific visual concepts via examples. For example, we can provide a set of input images to teach the model about our teammate's cat and then ask him to be visualized as a fantasy character. Prompt-to-prompt is a method to modify the prompt to Stable Diffusion while keeping the image visually consistent. For example, after asking Stable Diffusion to generate a photo of a dog with sunglasses, we can replace dog with cat and get a visually similar image of a cat wearing sunglasses instead. Feel free to check out all our generative AI guides at KerasCV website. Next, let's talk about Keras NLP, which unlocks natural language processing workflows with the same easy-to-use API. Let's start by training a sentiment analysis classifier to predict whether movie reviews are positive or negative. We instantiate a BERT classifier task model using the FromPreset constructor. One difference from KerasCV is that Keras NLP task models like BERT classifier include preprocessing by default. This means you can pass raw strings at both training and serving time without worrying about using the correct tokenization and packing methods. For this reason, it is best to call from presets on the task model itself rather than passing an explicit backbone. This will automatically give you a matching preprocessor class, which will tokenize and pad the input text to match the expectation of the backbone class. In this case, we choose the BERT base in uncased preset, which is one of the largest architectures trained on lowercase English data. This backbone has been pre-trained on gigabytes of text data to understand the meaning of words in context and extract more information from our labeled examples. You can find a list of all available presets in the class docstring or on keras.io website. After fine-tuning our model on a dataset of sentiment labeled movie reviews from IMDb, we can predict the sentiment of 2 new movie reviews. We can see that our first review, "What an amazing movie," is given a 99.6% probability of having a positive sentiment, while our second review is given the almost the same probability of having negative sentiment. KerasCV also offers text generation using popular models such as GPT-2 and OPT. Fine-tuning a text generation model is as easy as classification. Simply pass a dataset of text that you want the model to imitate, and the pre-processing will be handled automatically. Causal LM is a task model that predicts each token in an input sequence given all the preceding tokens. It is a canonical approach to training generative text models that can predict new tokens given a user prompt. In this example, we load a pre-trained base GPT-2 model using FromPreset constructor and fine-tune it on 300,000 news articles from CNN, the Daily Mail dataset. After that, we compile and fit the model like any other Keras workflow. Causal LLM tasks come with a generate method allowing you to specify a prompt and maximum output length to generate new text. Here we generate the start of a news article about snowfall in Buffalo, New York. Wow, that's a lot of snow, as you can see. We have now seen a number of high-level APIs to build state-of-the-art models with just a few lines of code. But what if we want more customization or to build something entirely new? The Keras ecosystem of libraries is built around the principle of progressive disclosure of complexity. This means that simple use cases should be simple and advanced use cases should be possible. We accomplish this by building up our highest level APIs from a set of lower level modules that are as well documented and easy to use as all of the models we have shown you so far. For example, suppose that your datasets includes relatively short text segments and training requires many passes through the data. In that case, the built-in preprocessor in BERT classifier may not be a good fit for you, since it will pad all sequences to the max length of 512 tokens and recompute the preprocessing in every epoch of training. For these situations, you don't have to fork our code or start from scratch. Our BERT classifier is built from customizable BERT backbone, BERT preprocessor, and BERT tokenizer classes that each have their own from preset methods. To access the preprocessor directly, simply call our BERT preprocessor class with the same preset name as the classifier and any custom parameters you want to specify, such as a shorter sequence length. You can then apply the preprocessing yourself. In this example, including caching so that the tokenization is not recomputed in each epoch. To avoid invoking the preprocessor twice in your workflow, simply set preprocessor to none in the task constructor, compile and fit the model like another Keras workflow, and you are good to go. Need even more flexibility? Want to build your own custom transformer-based classifier from scratch? KerasCV offers all the necessary primitives to build a unique NLP model in just a few lines of code. These primitives are the very same methods we use to build the state-of-the-art models you have already seen. Using the Keras functional API, the first step to creating a new model is to declare an input tensor. In this case, our input is a variable length sequence of token IDs. We then pass this sequence to an embedding layer that learns a unique vector representation for each token ID and sequence position, returning their sum for each token in the sequence. We then pass the embedding output to a stack of configurable transformer encoder layer that apply a sequence of multi-head attention and feed-forward layers to the input. The output of this stack is our final sequence representation. To produce a single classification output for the token sequence, the common practice is to put a placeholder token at the beginning of each sequence and pass this token's representation as the input to a feed-forward layer with the same number of outputs as classes to predict. As with any Keras model, we pass the functional inputs and outputs to the constructor to get a model instance, compile and fit the model like any other Keras workflow, and you're good to go. So that's it for our overview of KerasCV and KerasNLP. Here are some additional resources you can check out. In our next video, we're going to dive deeper into image classification with KerasCV. See you next time.